Hello, everyone. This is the Legacy of Socrates, 8th edition, and we are kickstarting this with Dave Farley. Uh, in case you don't know Dave, he's the author of Continuous Delivery and really is a thought leader in this field. He has a ton of experience with code bases of different sizes and teams of different sizes. He has a YouTube channel I really like because he shares a lot of nuggets of golden advice on many aspects of software development, including working with legacy code. So I'm really glad he's here today to talk about engineering practices and in particular explore the notions of testability and speed. And without further ado, Dave, the stage is yours.
Thank you very much, and hello everybody. This week's kind of a special week for me. I've been working on a new book for some time, and it was published this week. So it's the one on the top of the three books here, the Modern Software Engineering, and really that's kind of the theme of the talk that I want to do today. But what would it mean if we applied engineering thinking to software? I think that often when I think it's quite common these days for people to say software development is not engineering. And I think that's true of most software development. But I think that when we do apply some engineering principles to software development, we get what you'd expect from an engineering outcome. We get a better result more quickly and more efficiently. So what kind of thing does that take? And in part, what it takes is to think a little bit differently about what it is that we mean when we start talking about ideas like engineering. So what does the term software engineering really mean? I think often we kind of conjure up ideas like this. We kind of conjure up what it takes to do engineering for physical things. And that's understandable because most of the history of production for human beings has been in building physical things. But this isn't our problem. This isn't the problem that we solve in software. Software is kind of unique in several ways, but one way that's of particular importance. Our product, however big or complex our code base, the product of our work is a sequence of bytes, or at least can be represented as a sequence of bytes. And as soon as we have that sequence of bytes, unlike anything else in the history of our species, we can recreate that sequence of bytes perfectly for essentially free. The cost of duplicating that sequence of bytes is almost nothing. So our problem is not one of production. Our problem is not a problem of manufacturing things, of reproducing repeatable things to a cost, to a level of quality, because we can always do that for free, in essence, by just cloning the sequence of bytes. So our problem's something else entirely. I was at a conference recently, and Alan Kay, the inventor of object orientation, spoke, and he talked about what engineering meant in the context of software development. And one of the things that he said was that it was designing, building, and repairing things in a principled way. So what are some of the principles? The other thing that he said was that engineering was about designing for failure. It was thinking about the ways in which our systems go wrong, as well as of the ways that they need to go right. So engineering is not all of the same. It differs in different contexts, and it's not all about bridge building. One of the examples I think that we can learn a lot from at the moment is the very modern kind of hyper engineering that's taking place at Texas at the moment, where Elon Musk and his team at SpaceX are building starships, these ridiculously science fiction looking rockets that he aims to be able to fly people to Mars with one day. This is the biggest rocket ever built, and it's not yet fully functional, but the aim is for it to be completely reusable. So what does it take to do that kind of engineering? Well, it takes testing things, evaluating things in controlled circumstances, and making measurements, and breaking things. It means that you need to be able to try things out to to their limits and see what happens, and then try them out in kind of little small controlled examples again and evaluate them, and then things will go wrong. And this is what real engineering looks like. Engineering is not some kind of perfect bureaucratic process. We often think about it in those terms. My preferred way of thinking about engineering is that it's applying scientifically rational thinking to solving practical problems within economic constraints. So we're trying to really, solve practical problems. That means that our models, unlike science, our models don't have to be perfect. I think one of the mistakes that we often make as software developers is to think that what engineering means is some kind of illusion of perfection. Engineering is not the same as mathematics. We can use mathematical models to help us along our way, but it's not the same thing. It's a little bit rough around the edges sometimes. It's a little bit pragmatic sometimes. The models that we use are imprecise sometimes. And all of these are valid and make sense in the context of engineering. Nevertheless, it is control, it is disciplined. So one of the things that I think is important about engineering is that it's about exploration and discovery. That's deeply what is going on. Certainly the kind of design engineering that I think is closest to what we're talking about. And that's certainly what's going on in Texas at the moment with Elon Musk and his crew. It's about exploring the limits of our understanding in practical ways that allow us to make progress, and making that progress in ways that allow us to continue to explore and to discover new things. So I think that what that is, so this is equally true of software development. Software development is fundamentally an exercise in exploration and discovery. So we should optimize to be good at that. We should optimize, in fact, to be world-class at exploration and discovery. For that, I think that tells there are good models that we can learn from. And the model that we can learn from principally is that of science. We can take ideas from science because science is a field that is grounded foundationally in its ability to learn. I have 5 ideas that I think are fundamental to our ability to learn. And they start with iteration. Iteration is making progress in a series of small steps. We're going to work in small steps, understand the nature of those steps, gathering feedback as we go. And really, there is no learning without iteration in some form. We need to be able to try ideas out and understand what they mean. That gives us the ability then to make progress incrementally. We can begin when we don't know the answers. We can change the direction of travel along our way and still steer our learning towards the new goal. And that means that we need to start thinking experimentally and organizing our work as a series of experiments so that we can make progress, gather feedback on our progress, understand whether this is a step towards our goal or a step away from our goal, and work that way. And we need to be empirical. Engineering is deeply empirical. One of the examples, this is not math. I'm not talking about a bureaucratic approach here or mathematical perfection. I'm talking about the techniques of learning and discovery that we can use to evolve our understanding along our way. I would argue that any complex system of any kind, but certainly any complex software system, does not spring fully formed from some genius creator's mind. Instead, it's the product of steady work where we build up our learning and our understanding of the problem domain, of our design and whether it meets the needs of that problem, and the reaction to our users and our customers of the software, and our use of the tools that we're applying. And all of these things are things that we learn about as through the life of software development. So optimizing for learning, it seems to me, is absolutely key to be able to achieve these kinds of goals. Software development is, there's a second category of things that I think are deeply important about software development. If we want to be able to make progress incrementally toward our goals, then we also need to think about managing the complexity of our systems. If you think about software systems, they are amongst the most, if not the most complex devices that human beings have ever created. Certainly, if you consider the whole internet as a software system, that's the most complex thing that humans have ever built. The next most complex thing is probably something like the International Space Station, but that only has millions of moving parts. Software systems with millions of lines of code are quite common in big organizations and in big settings. And certainly the internet goes way beyond that. So software development is fundamentally about our ability to manage complexity. None of us are smart enough to hold all of this completely in our heads at any given time, unless we're working on something really simple and really trivial. The systems that we build outpace our ability to hold the whole thing in our heads. So what we'd like to be able to do is that we'd like to be able to manage that complexity in some way. And I've got some ideas about the techniques that we can use for that too. We'd like to optimize to manage complexity. So we need to treat modularity as an important function of our systems. We need to divide the systems up in a way so that we can make change in one part of the system without compromising other parts of the system. We'd like to be able to make change in one part of the system without worrying about other parts of the system altogether. And we can do that with all kinds of different systems. You don't need to worry about how my website works when you're writing a website, your own website. They're separate things. They're modular. They're independent of one another. And any big complex system looks like that. If it's well designed, it's going to be carved up into pieces where we can work more independently of other people. In order to be able to achieve that, we need to be able to draw lines of abstraction between different parts of the system. We'd like to be able to design an interface that separates one part of the system from another in a way that we don't care what's going on behind that interface. So we're going to abstract things. One of the tools that allows us to do that kind of thing is to focus on separation of concerns, focusing each aspect of our design so that it's focused on achieving one thing. We'd like each part of our code to be doing one job and doing that job well, and that makes it easier for us to be able to achieve these abstractions and this modularity that we seek. We prefer it if at these points where one module depends upon another, they are loosely coupled. They change, they don't force change on one another. And so there's something about these boundaries between our modules that is a little bit more important than the boundaries within the modules. So the boundaries between a module of our software, a service, or an app or something like that is going to be a little bit more well defended, a little bit better abstracted, a little bit more carefully designed than the boundaries between the classes and the functions that make up that module. And that gets to talking about cohesion. The things that are closely related, we want to be close together. My favorite description of high quality in design comes from Kent Beck, which says high quality design is about moving the things that are unrelated further apart. That's modularity. And the things that are closely related closer together. That's cohesion. And so we'd like to be able to use these things as tools to be able to achieve this. Now, I've just listed 10 things that I think of as fundamental defining characteristics of what I would think of as any engineering discipline for software. Think for a moment about what it means to build systems that are modular, abstract, have a good separation of concerns, loosely coupled, and are cohesive. Imagine for a moment think about the system that you work on regularly. Imagine two versions of it. Imagine one version that had no modules, no abstraction, no separation of concerns. All of the code is bundled together in one big lump. There's no loose coupling, that all of the pieces are tied together, maybe communicating through a set of global variables. A change in one part of the code could impact on any other part of the code. And bits of the code that are related are kind of not necessarily close together in the code base. If you've worked in software for any period of time, you've probably seen software that looks like that. I certainly have. Now imagine the opposite. Now imagine, whatever your technology, whatever the problems that you're solving, now imagine the opposite. Imagine your software system that's modular. It's divided up into pieces that you can identify and you know what they're supposed to do. It's got abstraction and it draws these seams between these different pieces that allow us to work in one part without worrying too much about what's going on in another. Each piece is focused on achieving one outcome and is loosely coupled with regard to the other, and the bits of that change together in our designs are closely held together in those same designs. So let's just think about that for a moment. Which of those systems would you prefer to work in? I know which one I would choose. I would choose the second one every time. So I think here that there's more than just these ideas as an abstraction of what software development is. These are tools that we can use to evaluate the quality of our decisions and the quality of our choices. Now, this isn't necessarily simple. There are trade-offs between all of these ideas very often. But we can use these to make decisions. If I make this design choice, does that improve the modularity or the abstraction? Does it make the separation of concerns better? Does it result in more loosely coupled pieces between our modules, or improve the cohesion? If it doesn't do any of those things, it's not improving the quality of the code, I would argue. And so these are tools that we can use. Similarly, the iteration and the feedback and the experimentation are also tools that we can use to figure out how we're going to develop software that looks like that. So I would argue that these are tools that we can use that will drive us toward better outcomes. If we steer our development to improve iteration, improve the quality of the feedback, speed up our learning through experimentation, and so on. And if we focus our design choices on managing the complexity of our systems, and so apply modularity, cohesion, and all of those ideas, then we're going to get better outcomes. And that's what I think engineering really means. So I would argue that we should focus on optimizing for learning and optimizing to manage complexity. There are some techniques that we can use to achieve those ends. So the first thing is that we can start to control the variables. This is kind of cross-cutting. If we control the variables, then that's going to limit the complexity, sure, within the scope of whatever we're looking for. But it also means we're optimizing for learning, because it allows us to do things like run tests. If you can't control the environment in which your test operates or the data on which it operates, it's not really a test, because you don't know what the result's going to be. So controlling the variables is an important idea. We'd like to make evidence-based decisions, and then and based on those, run the experiments that we've come up with to deliver for more evidence so that we can grow our learning. Another of these more subtle ideas that I think that we can learn from scientific style reasoning is perhaps the most profound idea in science, really, is not that we don't start out assuming that our answers are correct. Rather, we start out assuming that they're incorrect. So in software, we don't start out thinking that our design is correct or perfect or doing what we hope it will do. Rather, we assume that it's probably wrong, and therefore we need to figure out how it's wrong so that we can learn from that. That gives us a good way in to solving problems and to addressing the quality of our solutions. Find ways to falsify ideas simply with experiments rather than to prove that our code is good. However many tests, as an example of that, however many tests that I have, I can never be certain that I have enough tests to prove that my idea is good. However, I might always have missed something. But if I have one test that fails, I know that my ideas are not good enough, and therefore I can falsify my changes. This gets us on to testability. I think testability is one of these tools that we can use to achieve better outcomes. By driving our systems from the perspective of making them testable, we can get to higher quality code more quickly. So what do we value in good code? Well, first, rather obviously, the code has to work. But good code, as we've already discussed, is modular, it's loosely coupled, it's highly cohesive, it's got good separation of concerns, and it exhibits information hiding or abstraction. So what drives that kind of quality into our code? Before test-driven development, for example, I would argue that it's only these three things: the skill, experience, and the integrity of a programmer. You have to have the right skill to be able to put quality into code. Anybody can't do it if they don't have those skills. It probably takes a bit of experience to have learned the ways, what matters and what doesn't. And you need to care enough about the task that you're undertaking to bother to do the work to do a good job. And that's important. Those things I'm not dismissing those things, they're important. But let's think about testing for a moment. So test-driven development is a specific thing. Oops, sorry, press the wrong button. Let me catch up. So test-driven development is a specific thing. Test-driven development is not just unit testing. Test-driven development is writing a test before we have some code. So we're going to write a test, run it, and see it fail. That's red. And then we're going to write enough code to make the test pass, because we're in an unstable state while it's failing. And we're going to write just enough code to make it pass. That's green. And then we're going to refactor the test and the code to make them beautiful, readable, elegant, more generic, while we're in a stable state of having a passing test. So write a test, see it fail, write some code to make it pass, and then modify the code to make it the design that we really want. That's the test-driven development mantra. So what does it take to be able to write code like that? What makes the code testable? Well, obviously, code that's testable has to work. But it also is modular. We can't test code if we've got the entire system. There's too much going on. If we need to be able to narrow our focus so we can write these tests and evaluate these tests in controlled circumstances, controlling the variables, then we need modules that we can test to the boundaries of. These modules need to be loosely coupled so that our test is not too tightly coupled to the system, so that the code can change a little bit and not impact on the test. We'd like the bits of the code that are closely related together to be close together in the code, so that we can evaluate those in the context of the test. When we ask our code to do something, then it's going to do that thing. It's not got to communicate with lots of other pieces in order to be able to do that. So cohesion is good. A good separation of concerns. We'd like our test to be focused on particular outcomes and not just randomly asserting values for results. So we'd like to know what is going on. And we'd like to be able to talk to our code from our test and not care too much about how the code actually works, so that the test is a little bit more independent of the code. So testable code shares these properties of what we've just described as good code. So what that means, so let's think for a moment about what that means in terms of the impact on our design. It still takes skill, experience, and integrity for a programmer. You still need to be smart, you still need to do good design, you still need to do a good job. But now we've got this tool, test-driven development. We're going to write a test first before we've got any code. So we're going to make our life easier by writing code that is testable. Otherwise, we'd be done. Why would we do anything else? So we're going to apply test-driven development. And now we've kind of amplified the impact on these values that we ascribe to high quality in code. This is kind of like a talent amplifier. If you're a good software developer, then this is going to make you better. If you're a great software developer, it's going to make you greater. If you're a bad software developer, it's still going to make you a bit better. It's not going to make you a great software developer if you're bad, but it will make you better than you were without it. So there's not much like this in software development, I think. So let me give you a little example, a slightly more practical example of what it is that I mean. I'm going to change this car to be testable. This is a little class that's a car, and it's got a function in it called start. So my car creates a petrol engine. When we call start, we're going to put the car into neutral. We're going to apply the brakes, and then we're going to tell the engine to start. That's my code. So let's write a test for this code. So here's my test. Should start car engine. We're going to create a car. We're going to say start, and there's nothing that we can assert now. We could break encapsulation and get access to the petrol engine, perhaps, or that's horrible. That would be a vile thing to do. So I definitely don't want to do that. So fundamentally, this code is not testable. So let's just only focus on making this code more testable and seeing what the result is. So here's another car. This is a better car. And it's better in one particular simple respect. What I've done in order to be able to make my car more testable is define a point at which I can measure the behavior of my car. Instead of creating the petrol engine in the car, I've injected the engine through its constructor. So what does that mean? So let's write our test again as before, same code as before, other than that change. So let's write a test. So here's my test. Should start better car engine. So here's my fake engine. What's a fake engine do? Well, a fake engine allows us to measure the interaction of the car with this engine. In this case, I would probably usually use a mock or something like that to do this kind of thing. But in this case, I just wanted to make it simpler and just show you what's going on. So I've created a fake engine, and all it does is that when I say start, it records the fact that the start happened, and then I can query that later on. So here's my test. I'm going to create a fake engine. I'm going to pass the fake engine into the better car. And now I'm going to say start once more. And now I can assert whether the engine started successfully. So I've made my code testable. And there's the test, and the test is going to run. It's presumably going to pass. That all looks good. But what does this mean for the design of my code? Well, what I've done is that I've created a fundamentally better solution. So this is a more modular solution because I've moved the details of creating the engine outside the car. The car no longer knows about that. It means it's more loosely coupled with respect to engines. It only cares about the fundamentals of an engine and not the detail now. It's more cohesive. The bits of code that are related to the car are together here in this class, and the bits of the code that are related to the engine are not here in this class. They're somewhere else. That's good. That's a good thing. It's more modular too. It's better separation of concerns. This is focused on being a car and not worrying about the details of how to create engines as well as other things. So all of those properties that I've just mentioned have been just slightly tuned up a little bit by this move. But it also has a deep implication in terms of the practicality of the code that I've just written. Now, if I want to create a car in my system somewhere, I can create exactly the same car as before with a petrol engine. And it's going to work in exactly the same way that it did before, except that my new car was testable. But it's also more flexible because I could create a different kind of car with an electric engine and with no changes to the code of the car. Or if I'm some kind of crazy person, a better car with a jet engine. This is more flexible code. It's more usable code. It's code that we can use in different contexts. And that came simply by trying to make the code more testable. That's the kind of output that we would expect from an engineering discipline. That's the kind of amplification of our skills and talents, our working practices, that we would expect to see if we were doing a good job. The next is working experimentally. And we've already talked about that to some degree. We need to think about the building up the pieces of our system to allow us to make progress. And this is the first test of the methane breathing Raptor engine that SpaceX built and are now refining the development of over time. But you carry out things on test rigs, you try these out in controlled circumstances. This is the aerospace engineering version of a unit test. So we need to do those sorts of tests. And sometimes our tests will go wrong. Sometimes we'll be trying stuff out. Sometimes we'll be learning as we go. That's the nature of experimentation. We need to make progress in small steps. This allows us to reflect on each step, working incrementally, learn from those steps, understand whether our steps move us towards or away from our goals, and we need to gather feedback from those steps, and that allows us to learn more efficiently. It also allows us to make progress even when we don't know what's going on. There's one of the examples that I write about in my new engineering book is the idea of balancing a broom. Imagine that we were given the task of balancing a broom. There are two approaches that we could take to balancing that broom. We could calculate the center of mass of the broom. We could look at the rounded end of the broom and figure out where the center of mass passes directly through the point of contact of that rounded end of the broom, so that it balances on the table. We could then very carefully position the broom so we left no impulse, so that the broom balanced absolutely perfectly, and that would be great. It's not very stable, but it would work. And it's not very stable because there's only one solution to that problem, in essence. Or we could put the broom on our hand and we could start moving our hand around. That's the feedback-driven approach. So if we optimize for faster feedback, we'll make smaller moves. We'll make tiny little moves and we'll balance the broom perfectly. If somebody comes along and shoves us while we're doing that, if we're any good at it, we'll probably still keep the broom balanced. We might have to make a bigger move in order to be able to react to that change. But there are now many, many, many solutions to that problem. This is the way that space rockets balance on the thrust of their engines, by sensing small variations and making tiny corrections all along the way. It means that we can start off balancing the broom when we've no idea where the center of mass is or any of the other things. We just start balancing the broom. We just start and react. If we imagine being able to set some kind of goal, like balancing a broom, and then we just start in any direction, doing anything, but we have a means of determining whether we're closer or further away from our outcome, our desirable outcome, then we will hit the outcome, even if we only move in random directions. I'm not suggesting that we should only move in random directions, but even if we did, we'd still hit the outcome because we'd discard the things that took us further away and we'd prefer the directions that moved us closer. And over time, we'd get to the outcome. That's how evolution works. This is how real engineering works. This is how we grow systems incrementally in small steps. Working experimentally is also about predicting the results. We like to define what we expect to happen ahead of time and then test things and controlling the variables so that we can understand the impacts of our choices and our decisions and our experiments. Fundamentally, what I'm talking about here is establishing this process that's based around feedback. For software, we'd like to be able to have an idea, get that idea out into the hands of our users and figure out what they make of it. We use test-driven development at the center of this picture to get very fast, short cycles. Evaluate the releasability of our systems in the middle of these, and then get those ideas out to our users and see whether our ideas are good ideas or bad ideas, and correct. If we learn that our ideas are bad ideas, we stop doing that thing, we do more of something else. If we learn that they're good ideas, we figure out how to do more of the things that are good ideas. And that's how we build fantastic products. This is really what experimentation is. And it's practical, it's pragmatic, it doesn't have to be deeply complicated. This is a quote from Richard Feynman, nearly everybody's favorite physicist, if you are nerdy enough to have a favorite physicist like me. But he was great at quoting on the philosophy of science, and this is one of my favorite quotes. It doesn't matter how intelligent you are, if you guess and that guess can't be backed by experimental evidence, it's still just a guess. The next in my list is speed, and we can use speed as a tool. By optimizing to get fast, efficient development processes, we get to learn more often. This is the idea of cycle time that I've shown on the screen. These are two software projects. In one of these software projects, they couldn't make a single line change to their production system and get feedback in under 103 days. In another one, the other one was about 20 or 20 times more complex than the one on the top line. We could get the same feedback and get the answer in 57 days. This is using continuous delivery as a tool to get feedback into our development process, creating repeatable, reliable processes for releasing software, using high levels of automation to optimize to get that feedback, so that we can learn more quickly, so that we can experiment more effectively, so that we can control the variables when we're deploying things into test environments or production, so we can simulate the software in use more accurately. Continuous delivery is about optimizing our build, deployment, and test systems so that we take them from a commit to something that's releasable. The idea of a deployment pipeline, which is the picture on the screen here, is that it's the definitive statement for the releasability of our software. If we do a good deployment pipeline, then if all of the tests passing your deployment pipeline, there's no more work to do before you're happy to put this change into production. And so that's a fantastic tool and also a fantastic experimental platform. The first part of this is really focused on continuous integration. We want to optimize to get fast feedback into the development process so that developers can learn and understand the consequence of their changes. Does the code do what I think the code does as a software developer? And that's kind of the TDD bit of the part of the process. And then the rest of the deployment pipeline is really saying, is my software releasable? Is it fast enough? Is it secure enough? Does it do what the users want it to do? Is it resilient enough? And we'd like to get that feedback. If we optimize for the kinds of numbers that I'm putting on the screen here, that drives out all sorts of other good behaviors in our development process. We can't afford to have teams that are too big because the handovers will slow us down too much. We've got to automate nearly everything to be able to get this kind of levels of feedback. And this is optimizing to speed up our approach is a fantastic tool to drive a higher quality engineering into our process. In the talk that I referred to earlier, Alan Kay also defined engineering as design, simulate, build. And I think that's a reasonable take. I think that makes sense. I would argue that this is deeply what continuous delivery and deployment pipelines give us. They give us the opportunity to think about those terms. Fundamentally, this first stage in our pipeline is about the design of our software. Through techniques like test-driven development, it gives us feedback in fine-grained ways as well as large-grained ways on the quality of our designs more quickly and more efficiently than any other approach that I know anyway. Then we simulate our system in use under all sorts of different conditions to understand whether it's releasable or not. And finally, we release it into production. And if you are following continuous delivery, that's almost for free because we've already optimized to be able to do that very efficiently. I talked at the beginning about cloning sequences of bytes, and then the deployment tools of continuous delivery just optimize for that. I have a YouTube channel and I talk more about this kind of stuff. If you'll forgive me advertising, if you're interested in any of these ideas, please do take a look because there's a lot of ideas captured in various videos. I'm about to release my 100th video on the channel. So there's a lot of stuff there to be able to follow up. And my new book is available. I'm not quite sure whether the pre-order is just open because this week it's just become available for use. Try using this code to see whether you can certainly still use this code for paper versions if you'd like to get a cheaper discount off the new book, which talks about all of these ideas around software engineering in a lot more depth. Thank you very much. That's the end of my presentation.
Thank you very much. There's a lot of things to unpack from your talk. It's amazing, and we had people talking in the chat, and we already have some questions. So I'm gonna start with the most voted questions. People, you can add questions in the ask a question box, and also vote for the questions you would like me to ask. But we already have plenty, so let's get started. So the first question is, first of all, Dave, great talk. What about requirements engineering? Most times my client refuse to do it, so I'm doing it, but it's unofficial. In general, requirements engineering, is it useful in legacy project? And I think the question here is, what would you recommend when you are working for a client and that client doesn't really want you to do that?
Yeah, so I think part of the way that I think about this is, excuse me, I'm trying to switch the screen so that you can. I don't think you're getting a video. There we go. That's better. Maybe that's working now. So part of this is that we're the people that are responsible for doing a good job. We are the experts in software development, and so there's a degree to which it's up to us. I made a joke in one of my videos recently in that, you know, we don't say things like, last week I typed 3,562 letter E's. How many E's would you like me to type next week? So there's a line that we choose to draw about the degree to which we expose our working practices for other people to make decisions on. So if we are asking for permission to do good design, good engineering, testing, refactoring, those sorts of things, I think that's a mistake. I don't think that's anybody else's job to tell me how to do those things. My job is to do the best that I can to deliver the best outcome for the people that employ me in terms of the software that I create as quickly and as efficiently as I can. So I'm going to make those choices because I'm more of an expert in software development than they are, and so I assume that my guesses are probably better than theirs in terms of optimizing those things. Getting the requirements right, getting the requirements process right, is a fundamental of making the development process right. And this is more, this is not just about non-technical people telling us how that process should work. Their job is to make us as efficient as possible because we are the people that are producing the software. So it's a negotiation. We need to try and find out how we can get this organized in a way that makes us most effective. And we know that better than they do, so we've got to coach them. There are always the chances that you end up working somewhere where you can't make a change. There's a joke from Martin Fowler that he made several years ago, which is you either change the organization that you work in or you change the organization that you work in.
Yeah, exactly. And that is valid for a legacy project too. And I would say that most of the time you are likely to be working on a legacy project anyway. So yeah, you can introduce change, or eventually you can change company. Okay. Next question. Is technical debt a useful term in your opinion, or would we be better off talking about complexity, separation of concerns, information hiding, abstractions, or lack thereof?
I think that the term technical debt was introduced with, for good reasons. I think that the people that kind of started thinking about it in those terms were trying to explain a real problem. I think it gets misused a bit, and I think it gets abused a bit and misunderstood a little bit. The data is kind of interesting. The data on the productivity of software development is kind of counterintuitive in many ways, and my argument starts that the real answer to the question is that we're under pressure. We've got to deliver things really fast now. The real answer is, okay, well, what the data says is that you need to do more testing, spend more time on the quality of your design, and do more things like refactoring and all that kind of stuff. Not less, because the teams that are the most productive are the teams that score best on measures of high quality in design, good automated testing, all of those things. Cutting corners is not the route to producing software more quickly. Teams that score highly in measures of stability and throughput, that's measures of the quality of the code and the efficiency with which they produce code of that quality, spend 44% more time on new features than teams that score low on those measures. So cutting the corners, it's counterintuitive, I accept, but saying, oh, we haven't got time to do tests, that's like saying, I haven't got time to brush my teeth, and then all your teeth fall out at some point not far in the future. That's what happens. So the technical debt accrues exponentially quickly to the point that it kills you. You know, it's going to stop the project eventually. And I see lots of teams that kind of miss that. So the concept of technical debt can be useful under some circumstances, but I think it's also a slippery slope, because I think it gives people that don't really understand software development, people that are just saying feature, 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 an excuse to say, oh, well, we'll pay the debt back later, and they never do. And so those projects grind to a halt and stop. Again, so, you know, if somebody employs me to do a job, they're never going to convince me not to write tests. I'm always going to write tests, because that's how I work. And if they don't want to do, you know, that's how I'm pretty good at software development, and on the whole, I build better software faster than, you know, lots of teams and people do. And that's because I focus on the quality, not because I focus on the depth.
Yeah, exactly. And
sorry, I think you're muted.
Oh, can you hear me now?
I can't hear you.
I think okay, either I have a problem with classic. Adi, can you hear me?
Yes, I can. Yes, I can hear you. I can hear both.
Okay, so maybe Dave, you have.
Yeah, Dave wasn't hearing you, but it's not hearing me either, I guess. But
that happens. Remote stuff, connectivity, all of that.
Can you hear us now?
Not the headphones.
Yeah. So for the audience,
yeah. Sorry, I can hear you now. I'm probably echoey though.
Indeed.
Yeah, now there's an echo.
Okay. There's an echo now.
Okay.
Try again.
Yeah, okay, try now.
Okay, what about now? Oh, it's better. Oh, thanks, I'm back.
Good.
Thank you very much. And yes, I was just about to say, I also have this experience. Today I work for a startup, and we're like, hey, we don't know if we will be live in like 3 months or 6 months. And we do compromise, but I push for quality, because my argument is that, well, do you want to still be live and successful in 6 months, in 1 year, and continue to be successful? Like, we're building all of this, it's probably because we want to maintain that for a long time. And so we cannot cut corner everywhere. Otherwise, in 1 year, then it will be very risky for us to continue, and very unlikely for us to be able to continue successfully delivering features. So it's something you have to do at home.
Yeah, I think it's a difficult line to tread, and I like working in startups. I've worked in a few. The most efficient startup that I worked in was also the one. So we could build software faster than any place that I've ever seen before. We were doing some complex stuff in building financial exchanges, and that's the most efficient team that I've ever worked in. And we were also the most highly focused on quality. So I'm not quite sure where the line is precisely that you draw between just working with high quality and, you know, sacrificing some quality to move faster in the short term. I'm pretty convinced that you just work with high quality, and that gives you the speed. So even in a startup scenario, you still should be aiming to optimize over a time horizon of, you know, probably months rather than days, you know, because months is the cycle. You're not going to kill software development. You know, you're not going to build anything significant enough in less than a handful of months, probably. And so, you know, that's the kind of time horizon that you want to optimize over, and that is enough time for bad quality code to start to trip you up.
That's true. Okay, we are running out of time, so thank you very much. There are other questions, what I will do is I will send them to your Twitter. So then you can reply there and people can follow you on Twitter and get the responses there. Thank you very
Great,
much,
thank
Dave,
you.
for being here. And we're going to take a little 10-minute break. We will set up Barry O'Sullivan, who just joined, and we will be back for a new topic.
Great, thank you very much. And thank you everybody for attending my talk today.